Hi, I'm Gary, and I want to show you how I use Cloudy. Welcome. Today we're going to look at the first plot we'll create using the save files in our M16 model. So I'm armed here with a copy of Excel and a terminal. So we set up our M16 simulation where we had several save commands, and today we're going to make a plot of the first one of them. So let's remind ourselves uh, what we have here. I'll grep on save in the m16.n file. So we see four lines that have save commands. Today we'll work with the save overview file, very, very important file that gives you an idea of the temperature, ionization, and chemical structure of a cloud. Tomorrow we'll talk about the save continuum, and it's a way to show the emission that observed from a cloud, what you would see with a telescope. And next, we then do save line emissivity, and that will allow us to make a synthetic spectrum of what M16 looks like on the plane of the sky, with the brightness increasing to one side. And finally, save ages is a way to say some time scales that the cloud will sim. So what we'll work with today is make some very rough plots of the overview file. So what I'm going to do is a pasteboard copy from m16.ovr. So the file name m16.ovr is in double quotes on the save command. And so that means save this output into whatever is in that file name. Each one of them has the word last. Remember, we're doing two iterations. We only want to report the last one. So I've now copied the contents of the overview file into the clipboard, and here it is. So the file is tab delimited, which makes it very easy to work with spreadsheets and also very easy to work with database programs. So if your browser will accept, your editor will accept tab delimited files, but you may have to give it a few hints about where the tabs belong. The first column is the depth into the cloud. So the Cloudy works by starting at the illuminated face, dividing the layer into thin sheets, and then determining everything in each one of the thin sheets. And it adjusts the thickness of these zones so that things are fairly homogeneous within it. So this is the very first zone. This is the middle of the first zone. So this is 5 to 12 centimeters away from the illuminated face. So as we go down, you can see the depth is increasing. The total thickness of the cloud that we modeled is 2.37 times 10 to the 17 centimeters. There's 3 times 10 to the 18 centimeters in a parsec. So this cloud was about a little under a tenth of a parsec thick, which is about what's observed. So these are the zones increasing. This is the kinetic temperature that's uh, derived from the equations of thermal equilibrium. So it's starting out at about 8,000 Kelvin, which is kind of typical for a H2 region in this part of the galaxy. Let's make a plot showing the temperature as a function of depth. So I've selected these two. I'm going to now copy them, insert chart XY, and this shows the temperature is the vertical axis, and this is the depth into the cloud. So this profile that we see is pretty standard. So what's happening is the beam of light is coming in from the left, going into the cloud. The beam of light is being attenuated in a particular way that we'll discuss. This part of the cloud, the first half of the cloud, is fairly isothermal, not very different from 8,000 Kelvin. And then as the light is extinguished, as you go through the layer deeper and deeper across the layer, across that atmosphere, more and more light is removed by the gas. So very little starlight penetrates. Paradoxically, it actually gets hotter, and then all the ionizing radiation is absorbed, and the ionization comes crashing down. It becomes an ionization front. This ionization fronts are also where it becomes very cool. This calculation stopped at a temperature of 4,000 Kelvin, because that's the default stopping criteria. We'll talk about how to tell cloudy when to stop integrating later on. You can see the zones are changing their thickness. So across here in the middle of the cloud, things are pretty close to being isothermal. And the zones get very big because it doesn't need to resolve changes. And then where these changes are starting to happen, especially here near the ionization front, this is a region where the ionizing radiation is nearly completely removed. The zones become very, very thin. Let's look at some ionization plots. It's called an H2 region because mostly hydrogen is ionized. So this is atomic hydrogen, H1. This is ionized hydrogen. These numbers are ionization fractions. So there's a number between 0 and 1, and it tells you basically the fraction of hydrogen that's ionized and the fraction of hydrogen that's atomic. So this layer, this first zone, is nearly 100% ionized, and only a tiny fraction is atomic. And so let's have a look at what the ionized fraction, the units are very different from this temperature plot. So we're going to have to make a new plot. Let's pick out the H plus and the depth. So this shows the depth in centimeters, and this is the fraction of hydrogen that's ionized. It's referred to as an H2 region because across this entire layer, hydrogen is fully ionized. And then the ionization front occurs and it becomes atomic. Let's put atomic hydrogen on this same plot to see what's going on. There we go. And so across most of the layer, there's almost no atomic hydrogen at all. You get close to the ionization front, you can see it becomes atomic. So the PDR is a region which is predominantly atomic. So this is getting into the PDR. Let's look at some of the ions that make really strong emission. Usually the strongest line in the optical spectrum is the O3 5007. So I went over there and I selected O3. And now I'm going to put the oxygen double ion across the depth. So we see here, it starts out at 80% oxygen is O3 or O plus 2. And as we go deeper into the cloud, the radiation is extinguished and the oxygen ionization goes down. Let's go see the other strong line that can be made here. The O2 ion, this is the ionization fraction of O2, and that produces the bright line in the near UV, the FUV, that the 3727 line. So the blue is O plus. So you see oxygen is mostly double plus at the illuminated face, 20% or so singly ionized. As you go into the cloud and the radiation field, the starlight's attenuated, the ionization is going down, and then finally the O2 line, the O2 becomes very strong. So we see in the emissivity file, in a couple of lectures, we'll see how the spectrum changes across this layer, and we can compare that directly with observations. So this is the overview file. It has a lot of information. Molecular hydrogen is here, carbon monoxide, other information. It's a good idea if you want to figure out, roughly speaking, what's happening in the model. So tomorrow we'll use a much better plotting program. We'll use Jeremy Saunders' VIEWS program, and we'll create some publication-ready spectral plots that would show what you would see with a telescope.